Good afternoon, everyone. I will give update on this project. This is basically for solar energy harvesting. So the research team is myself, Dr. Yu, and Dr. Shashank Priya. And primary research question is to increase the efficiency and stability of this dye-sensitized solar cell using environmentally benign materials. So the significance of this is that this kind of cell can work indoors, low light conditions, and then this is very less expensive if we compare the most popular silicon cell. So this is about 10 times less expensive, and then other things I will discuss in the so highlight, we fabricated this dye-sensitized solar cell on hard and flexible substrate, and then we want to increase the efficiency of this solar cell using various strategies, and one of them is upconversion. So these are the kind of particles which can absorb the light which is not being used with the dye we use. So this is IR region. So these particles can absorb and this convert to visible light, and then dye can absorb. So this light is even available during nights. So this cell can effectively work during night too. And then funding still we do not have the decision, they are pending. And so these publications, and then intellectual property, we do not have any patent yet. So once we have this successful integration of a conversion layer in the cell, we already have, then we expect to have patent. The collaborations, this is Dr. Zhang, Korea Institute of Energy Research, and then Dr. Kumar, Indian Institute of Technology, Kanpur. So objective of this work is, again, to increase the efficiency and stability of dye-sensitized solar cell using environmental benign material. And then there are several strategies, these strategies we follow to increase the efficiency. So simply I will explain this. So we have two electrodes here. This one, this is TiO2. Basically we use TiO2 semiconductor. And then this is counter electrode. So this we can see here photon. This is dye here. So dye is just excited here, and then we have the electrode in excitation level, and this is just transferred to the conduction band of titanium, and then it's flowing through the circuit. And there we here electrolyte, and then this is regenerated, and this electron is flowing like this, and then cell is this working. So some of the limiting processes, like if we have this light photon here, and the dye is excited, and now electron is here, and this is injected to titanium. If we get this electron perfectly to the circuit, then we have no problem. But we have the several processes, like this electron division takes place to the titanium, and then electrode is switching, and then we have recombination processes like back recombination to electrolyte, and then dye, and these processes are at competition level. Like this is microsecond, this is also microsecond. So this process need to be addressed. So if we see the efficiency on the flexible substrate, then we have 5.21% efficiency. This is for the lab test with small cell, not for the module. So these are the various modules and the process how we fabricate the cell. So this is flexible substrate, ITOPA, and this here we can see the TiO2. This is TiO2 coated flexible ITOPA, and that is platinum coated, and this is complete module. And then we have several flexible module here. So how this upconversion particles can enhance the efficiency. So if you see the absorbance spectrum here in the beyond this visible spectrum and IR region, then we have the absorbance with this material, and then this we have controlled the absorbance, and here is the 50 milliwatt laser, and the excitation wavelength is 980, and with that laser we can see here we have this emission in the visible range. And the dye spectrum is, absorbance spectrum is like this. It comes up to 730, something like this. So this comes to the dye absorption spectrum region, and the dye can absorb this spectrum, and then these photons can be converted in this conduction electrons. So the dye can be used, and this we can see here in this region. So this is just Raman is not related to efficiency. We just try to see if it's any structural change, but we could not see the structural change. So to know that's just the cause why this high emission is there. So this the local structure is not changing, and then this is the morphology of the particles. So we can have the control of the size of the particles. So we can use them as emission particles, and then we can use as scatter particles. So to control the light and then control the emission intensity. So the future work includes the integration of this layer and to increase the efficiency further. So then you will test this cell in different conditions like inside the room and another condition after we integrate